Okay, so we're recording the AP review session on Wednesday, April 28th, 2021. We're talking about the Lavender packet multiple choice non-calc. More specifically, we're looking at 2008 multiple choice. And again, this is without a calculator. And let's look at number 1. So here to ask to find the limit of a rational expression. What you want to do is try to imagine what the leading term would be. That's not hard. You simply multiply 2x by negative x, which is negative 2x squared. And of course, the other terms you'll get as well, but they're not going to have as high of an exponent as x squared. So put plus dot, dot, dot. Down below, you have x squared as a leading term plus dot, dot, dot. So whenever the degrees are the same as what they are here, you simply take the ratio to leading coefficients, and that's why the answer is -2. Now, what if I had this happening? The answer would be y equals 0. Or what if I had this happening? And it's non-existence because it just goes up forever or down forever. So just so you know, be mindful about the degrees for both top and bottom. This one here, just so you know, A is a trap. That is a total trap answer choice. Because we know the integral of 1 over x dx is natural log of absolute, and it should be absolute value of x, by the way, plus c. That we know. But this really is like saying x to -2 power, right? So add 1 to the exponent and divide by the exponent, and then plus c. So it's -1 over x plus c. And that's why it's going to be d. You can't do that for 1 over x because obviously if you add 1 to -1, you get 0. And if you divide by 0, that's undefined. So that's what we get, that's a special case, and we get ln for that one. So be careful, A is a trap. The answer is D. Okay, for 3, this is a derivative. It's going to involve product rule and chain rule. So what do? Well, I'll call this like F, or I don't know, call this like maybe G, call this like H. So that's H of X, that's G of X. So it's going to be G prime times H plus G times H prime. Easy peasy, right? So the derivative of x minus 1 is just 1. 1 times x squared plus 2 cubed plus G, which is x minus 1. And that's where the fun begins. You got a chain rule here. So if there's a color that stands out. So you move the 3 to the front, keep the inside intact, drop the exponent by 1, and then multiply by the inside. There you go. That's what you do. You do have to clean up a little bit. So you get that plus 6x, x minus 1, x squared plus 2 squared. And you have x squared plus 2 squared that can be factored out. And that's x squared plus 2 plus 6x times x minus 1. I know it's going to be probably something like C or D. And then we have x squared 6x times x minus 1, so you get 7x squared minus 6x plus 2. So there you go. You get D. So hopefully a lot of this is jogging your memory. And then finally, we have a integral here. For those who are D period, 2 might have been a little tough because you have, well, we kind of started talking about that yesterday. 4 definitely will be more next week, which will cover the D period. Or maybe, yeah, I think next week, not quite. No, I think maybe the end of this week. So you could break this up into 2 integrals, sine 2x dx plus the integral of cos 2x dx. Now, integral of sine is going to be negative cosine. However, you have a 2x here. Something called a u substitution. You guys might remember, or those who haven't seen it, I'll just teach it to you right now. So you let u equal the expression in the inside of sine. You take derivative with respect to x. You isolate the x. So now you have integral sine u with d over 2. You integrate that, you get negative cosine u times 1/2. Or negative 1/2 times cosine. You bring the 2x back in. So it looks like B is going to be the winner, because then for the next one, integral cosine u times d over 2. Integral cosine sine, because derivative sine is cosine, sine u times 1/2. So we plus 1/2 times sine 2x. And of course, don't forget the plus c at the end. So that's what I'm saying. These are very predictable. They're not terribly hard problems. Just gotta remember it's just more conceptual than anything else. So you can see we have some limit problems. We got continuity. We've got more derivatives. We got something with linear motion. FTC. This is a great FTC problem, especially involves EVT, extreme value theorem. That's a great one. 10's a good Riemann sum problem. 11's good from section 5.3, where we had to look at the graphs of derivatives. Chain rule for 12. 13 is another chain rule one. 14 is really understanding concavity. Here we have another U sub for number 15. 16 is implicit differentiation. So we got a lot of good stuff here. What's 17 about? That's an FTC style problem. 18 is kind of a little more critical thinking. 19 is more limits. Yeah, we just got a lot of good stuff here. So anyway, let me stop the recording. Actually, maybe I'll just stop the recording. No, okay. Let's do some more practice here. I'm going to share my screen again. So I'm going to kind of jump around a little bit. Oh, why am I going to 2003? Hold on. Or how that happened. Okay. So I'm going to do some FTC style problems. Just make sure you guys are kind of comfortable with it. I'm going to start with number 7, because 7 is totally about fundamental theorem of calculus. Then we have you guys try a couple, and then we'll talk. If we look at number 7 from 2008, you're given the velocity of a particle, and you want to find the position of the particle t equals 1. Now, here's what we know. We know that v of t is the same thing as s prime t. We know this. And we also know, because of fundamental theorem of calculus, if I integrate a derivative from a to b, the integral and the derivative knock each other out, so it becomes s of t, but I'm plugging in b and a. So that's FTC at its finest. That's exactly what we're doing. We're doing the fundamental theorem of calculus. So we're doing the derivative, the integral of the derivative. they undo each other. But because you have the limits of integration, we plug them into the antiderivative s prime, which is s. S is the antiderivative of s prime. Or we could say s, or position, is the antiderivative of velocity. And s prime is velocity, so that's why I'm doing the definite integral. Well, what is my velocity function? It's 3t squared plus 6t. Where are my limits of integration? Well, you're told the position at t equals 0, and you want to find a position at t equals 1. So I'm going to do 0 and 1. And that's just going to equal s of 1 minus s of 0. So I'm really just emulating what I have right above. S prime is v. V was 3t squared plus 6t. My time values, I have 0 and 1. So equals s1 minus s0. Well, s1 I don't know. I want to find that. S0 I know is 2. I know the position is 2 at t equals 0. And if you integrate this, remember we add 1 to the exponent, so 3t cubed over 3 plus 6t squared over 2. And don't worry about the plus c's because it's going to cancel anyway. And then you're going to plug in 0 and 1 to do that little like notation to show you're plugging 0 and 1. Fortunately, those cancel. 4% becomes 3t squared. So you got t cubed plus 3t squared. So you're going to plug in 1. So 1 cubed plus 3 times 1 squared minus, and you just get 0 plus 0. Okay. The left side, if you do it carefully, should be 1 plus 3, so you should get 4. Equals S1 minus 2. So S1 will be 6. And there you go. So the answer is 6. So that will show up several times, something like that. Questions about number 7? Okay. So here's what I'd like you guys to try, and then how have you put your answers in the chat. Definitely want you guys to try number 9. And because they're asking for the greatest value, and so if we think about G prime is going to equal F, right? This is FTC, G prime is going to equal F. So we'll need to test the endpoints, which will be, looks like -3. No, sorry, -2, because we're starting at -2. Actually, never mind. No, we are testing -3, because -3 is an endpoint here. -3 and 2. X equals -3 and x equals 2. And also critical points, where G prime equals 0. Or will F will equal 0? Well, obviously from the graph of F equals 0 right there. So a critical point will be x equals 1. And then you plug these in to the function. Then you make a little table and say, okay, I'm going to test my endpoints of the G function and test critical points. So you're going to do G of -3, so you have to integrate that. And you have to use area, right? Likewise with G of 2 and G of 1. So I'll let you guys try that one, number 9. Also, I'd like you guys to take a look at number 17. 17 is also a fundamental theorem calculus problem because G of x equals integral, so G prime equals F. That's also, and it's dealing with points of inflection. So I'd say 9 and 17. Try to see if there's any other FTC style problems here. Nothing that really stands out. Yeah. So 9 and 17. Go and try those. Give you guys about 5 minutes. I'll pause the recording. If we have an answer, put in the chat. If you're confused, put in the chat, speak your microphone. I will turn off the recording because I don't want recording just long pauses. So, but 9 to 17, I want you guys to try. There's a question in the chat. Oh, so we already got an answer for 9. I will private chat with you, see if you got it. Go try 17. So for number 9, the answer will be D. The reason why it's D is because, again, our endpoints were -3, 2, and our critical point was 1. Remember, G prime equals F. So the critical point was G prime is 0 or F is 0, which is clearly at X equals 1. The endpoints are pretty obvious from the diagram, -3 and 2. Make a little table again. Put -3, 2, and 1. So if you integrate that, you're finding this area. This area is above the x-axis, but you're going from right to left. So I know it's going to be a negative area. If you want to find it exactly, that's 1 and that's 0.5. We'll say it's -0.5. Sorry, -1.5. Now, if you integrate this from -2 to 2, you're going to find that these areas cancel out each other. This is an area of 1 and -1. This right here is 2 and 1. So you get 3. Okay. If you integrate from -2 to 1, you're only looking at this region right here, which is going to be area of 4. And that's why we get the greatest value. So it's an extreme value theorem problem as well. So it's a great way of combining 2 theorems, FTC and EVT. So the college book can get a little creative like that sometimes. Now 17. Again, we want to establish that G prime equals F. And by the way, I mean, it's multiple choice, so it's not like you're getting partial credit here. It's always going to write stuff out. You're totally on horizontal tangents for the graph of F at 2 and 5. You want to find points of inflection for G. Now remember, points of inflection happen when G double prime changes sign. Or when F prime changes sign. So I have to look at tangent lines on F graph. Before I was looking at Y values, I was dealing with G prime and F. Now I'm dealing with G double prime and F prime. So I'm looking for F prime change sign. Well, right now, from 0 to 2, my tangent lines are positive, then they become negative. Then they're negative before I get to 5, then positive after 5. So F prime changes sign twice at 2 and 5. And so that's why the answer is just G. Sorry, just C. So that's all. That's all you do for that one. So it's C for 17. Okay. So let's go do some other problems. Let's review maybe some of the tables and graphs derivatives I think are good. Yeah, let's do that. So let's take a look at number 11. Graph and function I've shown above, which of them could be the graph of F prime? Well, if I want the graph of F prime, I want tangent lines, right? Slopes tangent lines. My tangent lines are 0 here, positive here, but negative here. So I expect F prime to be positive here, negative here, positive here, 0, and 0. So definitely I expect x-intercepts at probably roughly -1 and 1. Looks pretty good to me for B. Definitely positive here, definitely negative here, definitely positive here. So B is a boy. And it's not true for the other ones. So that's why B is a boy for that one. Okay. That's 11. Questions about 11? Nope. Okay. So again, those you want to kind of go through quickly. Take a look at 14. Here they give you the second derivative. I'll give you guys probably 2 minutes to think about it. Then after that, then we'll do some implicit differentiation problems. We'll take a look at 14. And I'll pause the recording right now. So resume recording. Number 14, you have a f double prime in the table. So we know we're concave up here. We're concave down here. We're concave up here. And it's probably going to be a point of inflection somewhere along the way between 0 and 2. I don't know where exactly. Maybe it's that one. I don't know. Because I don't know what's going on with the second derivative between 0 and 1 or 1 and 2 exactly. But the fact that I do see a sign change, and probably like I was over here, I'm definitely going to see another point of inflection over there as well. So that's what the font says must be true. Okay. The graph F has a point of inflection at x equals 1. I don't really know. So you want to be careful about that. They kind of trick you with that one. Because remember, just because second derivative of 0 does not mean it's a point of inflection. You have to specifically see a sign change at that location. You have to have sign track, which means you need to have an actual function to do that. We don't have enough information there for D. I'm kind of liking E though. I think the concavity is going to change because yeah, it was positive 0, negative at 2. This is looking pretty good to me right now. Is it a local max x equals 1? I need f prime to go from positive to negative. I don't have f prime, I have f double prime. And just because f double prime doesn't tell you much about f prime. Is it decreasing? That's what f prime is negative. Okay, I don't know. Is f increase? I don't know. Is f prime is positive? I just don't know. So it's got to be E. So it's E for that one. Okay. So I'll do one more example, then kind of have you guys try a couple more, then we'll end the breakout session. Excuse me. Let's take a look at I think 13 is a good one. Actually, I'll start with I'll probably do both 12 and 13. I'll have you guys then try 16. So here, you're asked to find the derivative of this. So e to whatever is e to whatever was a chain rule. So you gotta do that derivative. Now remember, 2 over x is 2x negative 1. Do that derivative is negative 2 times x to negative 2. And there you go. And that's why it's D's and dog. For 13, they want you to plug ln x into your function first. So it's ln x squared plus 2 times ln x. If you know your log properties well, you can actually move that 2 to the front. And it's actually 4 ln x, but actually, you know what? Maybe I'm getting a little too cute here. Let's just back up a little bit. Because I don't see 4s in the choices, so. We'll just do that. So I do this derivative. That's going to be 2 times ln x, but then times 1 over x, you got to do a chain rule. And that's just plus 2 times 1 over x. So both have 1 over x involved. But you have 2 ln x plus 2 all over x. There you go. That's just A as an apple. So yeah, those should go by pretty quickly. Go and give 16 a shot. I'll give you guys about 2 minutes. We have about 4 minutes left for a breakout room. So let me pause. Resume recording. So let me talk about this really quickly. Then we'll come back to the main room. So derivative sign we know is because you're basically doing d dx both sides, right? as an operator. So you get cosine of xy, but then you got to multiply by the derivative of the inside. So be very careful with that. Equals just one on the other side, right? Now off to the side here, let's look at the derivative of x is 1 times y plus x times y prime. That's what we want. We want to isolate y prime. So coming back, so we can divide both sides by cosine xy. Subtract y from both sides. And then multiply both sides by 1 over x. And it looks like our LCD is x cosine xy. Sorry, this was the cosine xy there. So it looks like y should be multiplied to cosine xy, so I probably should be doing this a little bit. And so that's why I'm going to get D as in dog. That one. So very mechanical. That's what's happening there. You have all the answers in Schoology. It has all the answers for everything in the packets. I would suggest you guys do maybe more, I don't know, multiple choice problems. Maybe 2003, you could try that one. That's another one. Tomorrow, I think I'll do probably some free response. I'll kind of come back to that again. Maybe some more typical, maybe 2016 or 2015, look at those problems. So anyway, let's go back to the main room.